All right, welcome to Chapter 13, Section 2, called Probability with Permutations and Combinations. This is for Integrated Math 2 or IM2. So I'm going to be reusing some of these videos from a previous video, so the problem numbers may not quite match up, although you will see a title at the bottom to let you know which number it's supposed to be. It's just kind of a time saver there. All right, so just to get started here on the front screen, the first thing you should see is your due date. I don't see that on my teacher preview, but you will see it on your student screen. The second thing is the number of attempts. We always have unlimited attempts on homework, tests, and quizzes. Number of questions just tells you how many are on this particular assignment. Grading policy is always best score, so whichever attempt is the best one is one you get to keep. And partial credit is enabled, so if you answer one of two questions correctly, you get credit for the one question, or however many you answered correctly. This also, if I understand correctly, goes into parts of a question too, if there's more than one answer within the question. There's partial on there too. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. And what that means is once I click start, down here in the bottom right corner, there's going to be a submit assignment button. This is how we finish an assignment. So what that means on the last screen is you can't work on anything because Alex is going to lock all of your other assignments and even the resources until you click the submit assignment button. What it's trying to do is leave this attempt open for you and not close it. If you say close this screen and you're not done yet, or you close your computer, it's trying to leave the attempt open for you. So just make sure that when you want to leave this screen, whether or not you finished, you click submit assignment so that Alex doesn't lock out all of your other assignments and resources. That's one huge reason to click that button. Another big one is that it actually affects the gradebook when you click that button so that your teacher can see what you've been working on and hopefully it will improve your grade there. All right, on the side we always have three resources. We have explanation. Explanation tells us that we're going to lose our current question attempt because it's going to give us the answer to this exact problem. So it's not going to give you the answers unless you come type them in. Example will give you something very similar to what it is we're looking at and kind of walk you through the idea here. Make sure you read through background information, especially if you see this section. If you don't see the background information, it's kind of introducing something brand new. That's the idea. So you can scroll through. Once you're happy with that example, you can close it. You can open another example so that you can see another one worked through if you need to. You can also message your teacher directly from the screen so we know where to come help you, because it attaches a picture of this problem on the email. So it's a good way to get specific help on a problem. All right, let's go ahead and get started. All right, so in this section, we're going to learn about factorials. And that's what we call, when we see the exclamation mark in math, it's called a factorial. And what it is, it's a very fast way of writing multiplication. But it's a kind of different type of multiplication. So when I see 6 factorial, what it means is 6 times every number before it down to 1. So 6 times 5 times 4 times 3 times 2 times 1. That is 6 factorial. So it's just a very fast way of writing that instead of having to write this all out. But same thing with 10, so I'd have 9, 8, 7, 6, 5, 4, 3, 2, 1. Like that. And I'm going to change that for whatever reason to different color just so we have it here. And then I can do the same thing with the 8. So I have 8, 7, 6, 5. That's a 6, I swear. It's a very ugly 6. All right, there we go. 6, 5, 4, 3, 2, 1. And then I'm going to do the same thing with the second 8 there. I guess I'll go with yellow. 8, 7, 6, 5. Why did I write a 7? I said 5. Oh my goodness. 5, 4, 3, 2, 1. Okay, so I've expanded out this factorial. And like I said, it's just a very fast way of multiplying all those numbers before it. And it has to do with when we're computing some of our probability. This makes it a little faster if we understand this idea of multiplying all the numbers that came before it. These are like all the combinations of numbers that we could have. They are not giving us a calculator to do all of this crazy calculations. So how do they expect us to get this done? Well, what they want us to notice is if you expand it out, like we have here, then we can do a whole lot of cross-canceling. So I can cancel 1, 2, 3, 4, 5, 6, 7, and 8. So the entire 8 on the bottom cancels out. And then I can cancel 1, 2, 3, 4, 5, and 6. So the entire 6 on the top cancels out. And then almost the entire bottom cancels out here. Before I even start multiplying pieces, I can actually cancel a little bit more because 10 can divide by 2 and 8 can divide by 2. So I can cancel those just a little bit more. And I believe that's about it for the canceling. Now I'm just going to say, well, what's left over? I have 5 and 9. Those are my only two pieces on the top that are actually left. So that's 45. And then on the bottom I have 4 times 7, which is 28. So I believe that they will be perfectly fine with us leaving it that way. Don't think they're going to want us to turn it into a decimal. Let's check. Ta-da! Yeah. So they're perfectly fine with us leaving it as an improper fraction. They do give you the option to turn it into a proper fraction or a mixed number. But I think improper fraction is a little bit easier to look at in certain situations for this stuff, especially when we're looking at probability, because this would be 45 to 28 of some kind of event. So sometimes we'll turn it into a percentage as well, because that actually can be a little bit easier to look at with probability too. Okay, so now we're going to look at what this is called permutations and combinations. So we have a couple of different definitions here, and I want to make sure we go through. Always look at the example. It'll give you some background information here because you're probably not going to know what this stuff is right off the top of your head. And honestly, before this in math, we probably haven't gone over anything like this before. We haven't gotten this far into it. They start off very simple probability in IM1 or algebra sometimes, or geometry. I don't know if geometry regularly gets into any kind of probability. This would be a little bit more of an algebra situation, I think. So the expression is the permutation. So it means the number of permutations of n things taken r at a time. So it's just giving us very quick numbers when it's written this way. So it can be evaluated using the formula, the number of things, so the factorial, divided by the number of things minus the r at a time, and then the factorial of that. So let's go ahead and write these out because we do want these formulas. So I have NPR, so that's going to be the factorial of n over n minus r factorial. So these are permutations. And permutations are when the order does not matter. So how the event happens, how things are taken, is not going to change the outcome. A combination, which is what the C represents, so this is a combination, this does matter. The order does change things. So we want to make sure that we're paying attention, which one is which. In this case, this is a kind of a very simple idea. It's not necessarily going to matter because they're not giving us a situation to kind of deal with here. But the definition of each, we just want to make sure we understand that one has a very specific order and the other does not. So permutations, order doesn't matter. Combination, the order does matter. All right. Oh, and that was the other thing. I kind of skipped over it. So note that by definition, 0 factorial equals 1. So if you have the factorial of 0, it means 1. Also, we have that 1 factorial equals 1. So either way, if we have 0 factorial or 1 factorial, it equals 1. So we need to make sure we pay attention to that. All right, so let's go ahead and work these guys out. So with this one, I have P, and the N is 8, and the R is 5. So I'm going to go ahead and plug these in. So I have 8 factorial, and then N minus, 8 minus r factorial. So this is going to be 8 over 8 minus 5 is 3, right? So if I expand this out and I go 8, 7, 6, 5, 4, if I go 3, 2, 1, what would be on the bottom? 3, 2, 1, right, for factorial of 3. So they would end up canceling each other out. And I don't really have a whole lot of room. I can write them over here a little bit, but I'm kind of running out of room here. So 3, 2, 1. Well, the 1s would cancel, the 2s would cancel, the 3s would cancel. They would all cancel each other. So what's left over is this bit on the top. So they did give us our piece here. So I could actually go 8 factorial. They give us a little factorial piece here. And I can go divided by 3 factorial. So I can actually plug it right in. It'll let me click this. And this is on all calculators. Well, I won't say all calculators, but the calculators you have in class should definitely have the factorial button. And you can click the button and it'll, the equal button, it'll tell you 720. If I did 8 times 7 times 6 times 5 times 4, guess what? I also get the same thing because it canceled them out. So the calculator is going to cancel them out for you. You don't necessarily have to do that part, but just be aware that you can click the factorial button. All right, so for the combination, we have 6 and 0. So I can actually kind of type this whole thing into the calculator if I wanted to, like this. And that's going to be divided by 6 minus 0, and then put the factorial times 0 factorial, which is going to be 1, and that's going to equal, so it gives me 1 on this whole thing. So if we wanted to make sure on that one, we would have 6 factorial on the top. 6 minus 0 is 6. And then we have 0 factorial. Well, 6 divided by 6, all of the 6's are going to cancel with all the 6's. So we'd end up with 1 factorial and 1 factorial. And 0 factorial, remember that fact just reminded us 1 factorial equals 1. And 0 factorial equals 1. So we end up with just 1. That was a whole lot of 1's there, but so there's only one combination there with that requirement. All right. So we're going to choose 2 colors without replacement from the 5 colors. So we're going to make 2 choices just like we did with the other pieces there. So we have 5 possible choices on our first choose. We have 4 possible chooses on our second. So 20 possible outcomes. That's if the order if the order of the choices matters. So it matters which one I choose first and which one I choose second, right? So just like we did for that other one, if I chose red for my first one, then my second one could be blue. I could do red and green, I could do red and purple, or I could do red and yellow. Those are my possible outcomes for choosing red first. Well, if I chose blue first, I could have red, I could have blue and green. See, blue and green. I guess we would have to write that somewhere else, blue and green, just so they weren't kind of mixed up. I could have blue and purple or blue and yellow. If I choose green for my first one, then it could be green and red. I could have green and blue. I could have green and purple or green and yellow. If I choose purple for my first one, then I could have purple and red, purple and blue, purple and green, or purple and yellow. If I choose yellow for my first one, I could have yellow and red. I could have yellow and blue, yellow and green, or yellow and purple. So, and I know I wrote those kind of spread out as I went down, but again, RB and BR, those are the same thing. So I'd only want one of those. I'm kind of crossing it out, but here, instead of crossing it out, I'll circle it. So that's 1. That's 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you notice, it kind of cuts it in half because I'm choosing 2, so I'm kind of flip-flopping those numbers. So it cuts it in half. So I have 10 in which the choice does not matter. It doesn't matter if I choose red first or blue second, blue first or red second. It's the same thing. I have a red one, I have a blue one. So it's not going to make any difference. Okay. Let's keep moving here. So now we're going to have a probability. So we're actually going to look at a spinner. Sometimes they give you little marbles. And I know when we did this in class, I had to actually put, red, green, blue on the little marble so you could see it because it was printed in black and white. So it's very nice to see it in color on the screen. So we have a spinner with 10 equally sized slices that it has 2 blue slices and 8 yellow slices. The dial is spun and stops on a slice at random. What is the probability that the dial stops on a red slice? All right, so there's definitely some weird things going on here. Number one, this is actually very common. If you go to a fair and they tell you to spin a wheel and you can win a prize, a lot of the time the big prizes are hard to win because they either don't have as many spaces or their slice is much smaller than the other slices. So it's much harder to land on that piece. Well, this is kind of the same idea. There's only 2 blue and there's a whole bunch of yellow. I'm way more likely to land on a yellow than I am a blue, right? But if I'm looking at this one and it says, what's the likelihood that I land on a red? Well, there is no red. So the likelihood that I land on a red is 0. I can't land on a red. If it says you have to land on a red to win the game, well, that's a cheat. There is no red. So this one's definitely a little bit easier than some of the other ones that I've seen before. So here, let's see if we can look at one that's actually got a little bit more to it. So a bag with 6 marbles has 1 blue marble, 2 yellow marbles, and 3 red marbles. A marble is chosen from the bag at random. What is the probability that it is blue or yellow? So first, for probability, I need to know total number of outcomes. If I reach into the bag, what are the all the different marbles that I could choose from? So I have 1, 2, 3, 4, 5, 6. So I have a total of 6 different marbles that I could choose. And I want it to either be blue or yellow. So there's 1 blue and 2 yellow, so that's 3. And then I need to make sure I reduce that. They can both divide by 3, right? So these can be reduced down to 1/2. So make sure you reduce it down. So I have half or 50% probability, because it's half of the marbles are either yellow or blue. So this one's a little bit different, but that first one was a little bit interesting because it not only was lopsided with the number of blue to yellow slices, but it also didn't have any red. So that was a little different. All right. So we have a boxes filled with 2 blue cards, 3 red cards, and 13 green cards. A card is chosen at random from the box. What is the probability that it is blue or green? So same idea we just did. They're just not giving us a visual, are they? But they're giving us the same exact idea. So if I want to calculate the probability of pulling out a blue or green card, I first need to know how many cards total are there in the box. So I have 2 plus 3, that's 5, plus 13, that's 18 total cards. So I could choose any of those 18 cards if I reach into the box. And it's random. I want a blue or green. There's a ton of green. So 13 green and 2 blue, so that's 15 together because I have 13 plus 2 more. So I need to reduce this because they can both divide by 3. So 5 over 6. So it's 5/6 for my probability. And we can even think about this as the idea is every 5 times I reach, or 5 out of 6 times that I reach in, I'll get what I want. So it's a pretty good chance I'm going to get what I want. It's actually a lot harder to choose the red cards. There's only 3 of them out of all 15 that we want. So or that they're asking us to choose from. All right. Let's do one more of these guys. So probabilities of permutations and combinations. So we have, there are 7 acts in a talent show: an acrobat, a dancer, a guitarist, a pianist, a singer, a violinist, and a whistler. A talent show host randomly schedules the 7 acts. Compute the probability of each of the following events. Event A, the first 3 acts are the guitarist, the pianist, and the singer in any order. Event B, the guitarist is first, the violinist is second, and the dancer is third. Write your answers as fractions in simplest form. So we want to make sure, let's click on example just to make sure we understand what it is it's asking us to do. Because they're actually going to want a number here. They don't want us to write out, guitarist, pianist, anything like that. So with this one, it's kind of the same idea, but we have 9 people are taking part in a raffle. So here's our 9 people. And then it's the same idea. So we have event A. For their event, they're being specific. This person is first, this person's second, third, and fourth. And then event B, we have the first 4 prize winners are Anne, Kira, Ravi, regardless of order. Oh, so I missed her name because I thought it was a typo for a second. So same exact idea, just different scenario. Their talent show versus a raffle. So for the permutation, a permutation is an arrangement of things in a particular order. For example, suppose Amy, Ben, Kat, and Dee are to stand in a line. A permutation of ordering of the first 2 people in line is as follows: first Amy, then Ben. Another permutation comes from a different order: first Ben, then Amy. We could also have 2 other people from the group: first Dee, then Kate. Each of these is a permutation of the 4 people taken 2 at a time. So here is the formula for the number of permutations of n items taken k at a time. So we've already actually seen this one. They had r instead of k, but it was the same formula, wasn't it? From earlier in the section when we were introduced to this idea. So we're going back to this idea where we're doing factorials. N minus k. So this is the total number, and then this is taken how many at a time. So that matters when they're telling us, there's this many people, 9 people, and they're going to be selected 4 at a time. So that does matter. They're giving us some information here. So we can actually plug it into the formula and say there's 9 people, and we're going to take only 4 of them. And we can go through and we can cancel out or use our factorial on the calculator. Event B is a little different. That's a combination. So for it's saying combinations, we only consider the choice of people, not their positions in line. So first Kate, then Ben is the same as first Ben, then Kate. They were both chosen. It doesn't matter when they were put in line. So now we would use the combination. Equals n factorial n minus k times k. Like that. So we just need to make sure that we're using the correct formula for what it's telling us to do. So if the order does not matter, then we use combination. If the order matters, then we use permutations. So for our event, we have event A, the first 3 acts are guitarist, pianist, and the singer in any order. So this is going to be a combination. It doesn't matter if the guitarist goes and the pianist goes and the singer goes. Or if it's the pianist and the guitarist and the singer. Or the singer, guitarist, pianist. It doesn't matter. They're all going to go. Right? So that's a combination. And we need to make sure 7 is the n. That's the number of talent. And they're going to be taken 3 at a time. Like that. So now I have 7 factorial over n minus 3 factorial. Oops, it wasn't n, sorry. It should be a 7. I forgot to replace it with 7. 7 minus 3. There we go. and then 3 factorial. All right, so then we end up with 7 factorial over 4 factorial over 3 factorial. Yes, these add up to 7. Do not do that. This is multiplication. So we have 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. 3 times 2 times 1. So remember, this is this 3. And then this the 4. So they're separate. It's 4 factorial is 4, 3, 2, 1. 3 factorial is 3, 2, 1. So I can go through and start crossing these off. The 4s are going to cancel here. I have 6, and 6 is 3 times 2, so I can cancel 3 and 2 with 6. And now all I'm left with is a 1 on the bottom. It's all I have left. So I have 7 times 5 is 35 over 1, which would just be 35. So for my first event, there's 35 different possible combinations of these acts. For the second one, I have the guitarist is first, the violinist is second, and the dancer is third. So it matters in which order they're taken. So now I have 7, and I have 7 minus 3 factorial. So it's going to be 7, 6, 5, 4, 3, 2, 1. And then this would be 4, right? So 4, 3, 2, 1. So I can cancel all of these guys. All right, so now I want to multiply 7 times 6. Well, actually, I could do 7 times 5. That's a little easier because now I have 7 times 30. 7 times 3 is 21, and I can add a 0 in the end. So now I have a lot more possible outcomes if the order really does matter. If acrobat, dancer, guitarist is different than dancer, acrobat, guitarist. Even though I said the same 3 things, I said them in a different order. They're different because the order matters. So we're not eliminating those duplicates. Okay, so I totally forgot this step when I was kind of hurrying through the explanation there. So these are the total number of outcomes for each one. What I forgot to put on there is that we're not necessarily, they're not just asking us for the total number of outcomes, but it wants to know what's the probability of each event. So there are 35 possible combinations here, and each one of those is equally likely to happen. So what we say is it's 1 out of, oh darn it, I was hoping it would actually go into the fraction the way it's supposed to, like this. So we put that under 1 like that. So we have 1, let's see, can I, dang it. It would help if it wrote correctly. There we go. So 1 out of 35 and 1 out of 210. So I forgot to put it into the fraction, into the probability. We want to make sure we do that. So each one of the 210 possible outcomes for event B is equally likely to happen. So we say that each one has a 1 in 210 chance of happening. Or same thing with that first one. So we just want to make sure we put it in the fraction. So that was my oops. All right, so that was section 2. I will see you in section 3.